All right. So linear programming. Linear programming. So we want to quickly go over in a very basic introduction today is the theory and the formulation and how to use Cplex to do some basic linear programming. And I just realized I've forgotten something, but I'll get it during the coffee break and still do a fun little example. So the theory here. So what is the theory? So linear programming is a method of solving decisions. It's a way of making decisions using mathematics, and it is, I've always referred to it as the Swiss Army knife of business management because it has so many applications. It has so many applications because very often a large number of practical business questions are linear. They can be represented by linear things. The consumption of materials is linear. The consumption of transportation is very often linear. The prices in contracts you set are very often linear. You pay by the gallon for soda. You pay by the pound for meat. You pay by the pound for steel and coal and these things. And these are linear. So very often the expenses that you have to deal with, the decisions you have to deal with are linear in a business environment. It's also very powerful because we now have such wonderful computer systems that problems that are really quite relevant and quite practical can be solved trivially on your desktop computers, on your laptops. And so it's becoming really strong, really coming into its field today as a valid tool for nearly all business activities, all business planning and strategy. Linear programming has a rich history. It originates, really comes into its own as a tool during World War II. It comes into its own as a tool for the most basic things such as food rationing, determining the menus on the food ration cards for Great Britain during the war when food was so short because there was a naval blockade around Great Britain and every bit of food that came into that island was both expensive financially and expensive in terms of lives lost in shipping across the Atlantic. So they used linear programming to devise menus to determine, very similar to the exercise we're going to do at the end of this lecture, determine what the lowest cost menu would be for the citizens, and yet that was appropriate for their health and keep them alive and keep them fed and keep them going. So what is linear programming? So we have a single objective. We have to be able to define mathematically some utility function that represents our desires, our hopes and our goals and our comfort level and our things. We have to be able to develop some measurement mathematically that expresses that as a number. We have a single formula that does that. It might be a formula that represents profit. It might be a formula that represents cost. It might be a formula that represents how many vacation days we get in a year, but it has to have some kind of a mathematical structure that expresses a goal we're trying to achieve. And then the function, the underlying decision space for that formula has to be convex. And I'll explain that in a minute. It has to be convex. And all of these things, the objective function and the underlying space that we're using to fit this decision into has to be linear. It has to be a linear function. Let's talk about what that means here. So convexity means that whatever space you have, if you put 2 points in that space and draw a line between those two points, the line does not leave the space. And that's very powerful for how the solution methods for linear programming work. The solution methods for linear programming, typically, there are a variety of other advanced ways of doing it, but the most common ways they do it are they actually trace the surface of the space. They trace the surface of the space and they look for an improvement. And if the space is not convex, then when the thing is tracing around the surface, it gets into a dip or a hollow and it can't get out of it. It can't climb its way out. It doesn't know which way to go to climb out of it, to find the improvement, to find the better space. So convexity is very important to making all the things we assume about linear programming work. Here's a space that is convex and linear. It is convex. Any place in here, if I put 2 points in the space anywhere, and I draw a line between those 2 points, that line stays inside the space. And And by the way, when I say the space or the feasible region, I include the boundary. So the boundary line is included in the feasible region. Not just inside the boundary, but it's up to and including the boundary is in the feasible region of this space. And it's linear. All the surfaces on here are flat. So we have these flat, pointy shapes that are linear. The equations that could represent this space are all linear. This is linear. It's still flat surfaces, but it's not convex. It has a hollow spot right here, and these 2 points here, a line drawn between them, the line leaves the space, so this is not a convex space. This can happen if you have various kind of decisions or constraints that have step functions in them. Example of a step function, an insurance rate on your car that changes if you hit a certain mileage level. Like they say, well, if you do 10,000 kilometers a year or less, this is your insurance rate. You go over 10,000 kilometers and suddenly your rate goes up. It's a step function. And you try to represent that here, and it creates a discontinuity in the feasible region, and now we have a non-convex space. There are ways we get around that in advanced formulation. We do these kind of funky things where we abstract the space and shift things around, but that's an example of how you might end up in a situation where the space is not convex. And then this space is convex, but it's not linear. And of course, there are many real-world situations where things are not linear. Acceleration is not linear. The acceleration curve, the speed curve of a vehicle as it accelerates is not linear. The consumption of energy is very often not linear. Lots of kinds of things. Electricity is not linear. But we very often get around this in business cases by linearizing the function. So even this space, it's not linear, but what we would do is we would clip this thing, and we would clip it. Take a pair of scissors or take a bunch of equation functions and take this round surface and turn it into a really rough surface composed of lots of flat sides and flatten out those sides. And then we would turn that into a linear program by linearizing the surface. We would introduce some amount of error by doing that. The final answer would be perhaps not exactly correct, but it would be reasonably close for most business decisions, for most kind of real-world practical applied decisions. I have a formulation mnemonic that I have taught for years and years and years. Because for those of you who have no previous experience in linear programming, for those of you who have no previous experience in mathematical programming, I suspect many of you are going to be exactly like my business students back in the United States. And you're going to make many of the exact same mistakes. You have many of the exact same struggles in trying to visualize and do this thing called linear programming. And the greatest challenges you're going to have are reading some written problem statement and absorbing the language of that problem statement and trying to then abstract that into a mathematical description. And it may even be doubly hard for you because, of course, many of you are now, we're going to have problem statements in English, and many of you, English is your second language. And so we're going to even have another layer of confusion on top of that. But very often, even when I had native English speakers, business students, hundreds of them, thousands of them over years, it was still the same problem, this ability to read the language and then abstract that statement into a mathematical function. So I developed this mnemonic as a way to kind of guide students and guide them into what they need to do to walk through a problem and develop the mathematical statement of what that problem is. It's a 3-word mnemonic: goal, control, limits. And you walk through this goal, control, limits every time you look at a linear program problem statement, and you want to walk through those steps and build your problem statement by walking through those steps. So here is our sample problem. Here's our sample problem that we're going to work here. This is a classic linear programming problem. This is the diet problem. In the literature, it's very often then referred to as a blending problem. This is the classic rationing menu problem of World War II. But then it also has application to things as diverse as blending feedstocks for animals, blending fuels for a coal-burning power plant, any kind of a blending problem, blending feedstocks for a plastic extrusion machine, all kinds of things where you have different ingredients that blend together to create a homogeneous product that then is feeding some other process. This very often is relevant and applies, and very often those mixtures are linear in their function. They can, when you mix these coals together or even alloys of metal together, very often you see a linear behavior in how they behave in the actual production environment. So this is a diet problem. And there's some information I need to explain. It's not too different from the labeling I see in Europe here at the grocery store, but maybe just a little bit different. So this information is nutrition information from these different foods. And here, you go to Netto, or you go to Super Grusin or something, and you buy a food, and it does have a nutrition label on the back, and it gives you some information. I don't know if it has exactly the same information. I know it has salt because I've looked at the labels for some food I bought, and I was concerned about the salt, so I looked at the salt. And I know sometimes it has vitamins. I'm not so sure and it does have calories. So I think you'll find a lot of this information on the food labels here at your local grocery store as well. And so what we have here is just a really simple diet problem with a very limited set of choices here. Eggs, you know what eggs are. I think we got those in Europe. Orange juice, you've drunk that, I'm sure. This you probably don't have. This is a cereal. This is a basic commercial cereal in a box. And you don't have this either, I don't think. Wheaties, I don't think you have Wheaties. Do you have Wheaties in Europe? I don't think so. It's kind of a cornflake, but it's not really. And it's not Weetabix. I'm not talking about Weetabix. So I don't know if I can, but anyway, these are two different brands of cereal. Two different brands of cereal, orange juice and eggs. And so we want to figure out a diet using just these 4 ingredients that's going to be fulfilling all of your nutritional requirements. And the question is, what should it be? What should you eat from this menu to fulfill your nutritional requirements? And so we've got some nutrition information. What I've done here is a long time ago, when I first started doing this lesson, I actually had students bring in nutrition labels from the grocery store, and we actually made a big spreadsheet. I had a huge spreadsheet with like 30 or 40 ingredients on it. These are just 4 I pulled out. But so this information is a little old, but these are US dollars, and these are the prices per serving, and these are the nutrition information either from the label. Actually, there's a label on the egg carton, so I got that from the egg carton too. This is all nutritional information from the label. And when I say serving, I think we have a similar thing on the nutrition label here in Europe. In the United States, the Department of Agriculture regulates this, and they actually define what a serving size of food would be, and then on the label on the package, they will say for that serving what is the nutritional content. So a serving, the classic kind of cheat in the United States is that if you buy a bottle of Coca-Cola, a serving of a bottle of Coca-Cola on the label in the United States is like 8 ounces, which is, I don't know what is in metric, but anyway, it's like 8 ounces, but the bottle itself, the typical bottle out of a vending machine in the United States actually holds like 16 ounces. So the cheat on that is the label says it's this many calories, but you actually have to get double that because the bottle contains more than what the label says it does. So this is an ongoing kind of under-the-ground controversy in the United States that labels on bottles should reflect what people are really going to consume, not what the hypothetical serving size would be. Nobody buys a bottle of Coke from a vending machine and then splits it. I mean, you drink the whole thing. So this is the price per serving based on that nutrition label on the back of the product in US dollars in this case. And then these are the nutritional values. This is calories, and you have a similar thing on the European label, so that's no different. This needs some explaining. These are percentages, and again, the Department of Agriculture in the United States determines what the recommended content in the diet should be for everybody. And then this represents the percent of that Department of Agriculture daily allowance. So the recommended percent of the daily allowance for a person in the United States. So these are percentage figures of the daily allowance in the United States. So anyway, so I've explained this data to you. So we want to formulate a linear program. We want to formulate a linear program for this problem. And we're going to write it up on the board in the correct format. And let me get a pretty color of chalk here. Let's see. Blue sounds good today. Blue sounds good. All right. So we're going to write this linear program. And the first thing we want to do is figure out what our goal is. What is our goal? What is our goal in this problem? Sorry? We want to formulate the diet, but that's not a... Is that our objective?
2,000 calories to spend as much money as we can. Minimize cost.
Minimize cost. That's our goal. Our goal is to minimize cost.
Yes.
And in most business situations, or kind of industrial situations, that's, you know, it's minimize cost or maximize profit. It's almost, one of those two is almost always where you're going. You know, certainly there are plenty of other real world situations where there's some other goal, but 75% of the things you're going to deal with in any kind of planning situation are minimize cost or maximize profit, one of those two. So we're going to minimize cost. Oh, there goes my chalk. What do we control?
Rates.
Hmm?
How much can we give?
What's that?
How much can we give to that people
We control how much we
give the food?
give, how much we eat, how much we consume. So we control how much of the food we consume. And on this table, where is that displayed? Servings used. So this is the area where we would write in how much we're going to consume, how much we're using. So these servings used, how much we're going to use. So we control the servings. So this control thing has a name in linear programming. It's called the decision variable. So we have a decision variable that we have to decide. We have to decide what the quantity of this variable is going to be. How many decision variables do we have? We have 4. We have 4 food ingredients. We have 4 food ingredients we have to decide on. That we have to decide the quantities. So there are 4 decisions to make. There are 4 decision variables. Now, in a lot of introductory texts, a lot of beginning texts, really basic kind of business school stuff, they'll say, okay, the decision variables are X, Y, and Z. Right? Well, we got more than 3 decision variables here, so that ain't going to work. And in fact, in the real world, in most real serious linear programming applications, we're talking hundreds or thousands of decision variables. In my research work, the work that I do, and the work you're actually going to see the second half of this lecture, because we're going to give you a taste of the real world here, no more baby stuff for you. I regularly do linear programs with tens of thousands of variables. 20, 30,000 variables, all the time. All the time. And in fact, the one you see today is going to be, I don't know, probably 300 decision variables, 400 decision variables. So obviously you can't go X, Y, and Z. Or you can't even go A, B, and C. You know, oh, I saw this funny joke once. I was in a bar in California, and they had things up on the wall. I saw this funny joke once. The sign said, "If Plan B fails, don't worry, you have 24 letters left." Of course, that's in English. Here in Denmark, I guess it would have to be 27, because we got 3 more letters in the alphabet in Denmark than we do in English. So anyway, so decision variables. So it's almost normal, completely standard that in big boy linear programming, we say the decision variable is X, and we put a number, a subscript down below to say which one is it. You know, because you've got 10,000 decision variables, you're just going to have to say x1 through 10,000. So we're going to have 4 decision variables. One, two, three, and 4. And let's assume we're reading from top down. So 1 is eggs and 4 is Wheaties, and we'll just keep that direction going through this conversation. So we have 4 decision variables. We control those decision variables. Our goal is to minimize cost. We now have enough information to do the first part of our linear programming, which is deciding what is the objective function. The objective function is what is describing the value of this thing we're trying to achieve. We are concerned with minimizing the cost of the menu, so we need a formula that calculates the cost of the menu. So this objective function is the cost of the menu. Very often, in a lot of literature, they will say then this is function z, and function z equals this thing. And we got to figure out what this function is. What is this function going to be? Noam, what's this function going to be?
x1 times price.
Sorry?
x1 times price.
Yeah, I'm ready. I'm going. Tell me what it is.
0.08.
0.8. And it's linear, so it's a multiplier and a positive. It's a linear coefficient and a positive. In addition, what's the next one?
0.9.
You guys are sharp. You're good. Usually it goes a little slower than this with my audience back home. All right, excellent. So there's our objective function. Linear, one equation, clearly stating our goal, what we're trying to achieve, the value of our goal.
Not actually.
Sorry?
Not actually. It should be put minimize.
Absolutely, right? So I'm missing a piece of information. I have the value, but I don't have any orientation yet. What's my direction? I'm minimizing, so very often you would write this something like, just put min in front of it. Say minimize that number. Minimize that function. That's my goal. My objective is to minimize this objective function. Am I done?
With the,
I'm all done, right?
no,
So what happens if I minimize that?
you will get just the lowest number, maximum 100%.
Get 0.
I get 0. I don't eat anything. That works. Solve problem. Problem solved. I don't eat anything. No, that doesn't solve it because we haven't finished reading the problem statement for one thing. So we haven't finished there, and we're not done because the thing we have not done in the mnemonic that I gave you is we've got goal, we've got control, and limits. Thank you very much. We need to figure out what the limits are. These limits are, in fact, now defining the feasible space, the decision space of our problem. What are the limits? Calories. What else?
Ratio.
Sorry?
Ratio percents cannot exceed the limits.
Is I need to know what the limits are. Calories is a limit. What else? What are the other limits?
Salt.
Salt.
D and C.
And vitamin D.
Vitamin D.
And vitamin C. So I have 4 limits in this problem. And they have values. They have limit values. Now, in a minute, we'll see that those are called the right-hand side. You don't know why yet, but you will see it'll be very obvious to you in a minute. So we need to figure out what the right-hand side of these limits are. The numeric value of these limits. What is the numeric value of the calorie limit? 2,000. Salt. What is the numeric value of the salt limit? 100%. Because I told you earlier, those are percentages of the daily requirement. So clearly the daily requirement is 100%, so that is how much of 100% each of those gives you for one serving. So our limits on these guys are all 100%. Now, the other thing that we can either do now or while we're doing the equation, but we just might as well do it now because the conversation is moving pretty good here. We need to set directions on each of these limits. That is, are these equalities? Are these less than or equal to? Or are these greater than or equal to? Those are basically our three choices. We don't really have any other choices. We have to have a direction on each constraint. Equal, greater than, less than, which one is it? Calories. What direction is that constraint? Equal. How did you know that?
More.
Your ass.
And actually, you're doing really well, actually. And part of that's because you're a graduate audience and you're a little bit more mature and you're smarter. When I ask that kind of question to an undergraduate audience, I kind of get, less than. So how did you, just for those who may be too embarrassed to speak up, how did you know it was equal?
Oh, 2000.
So that's exactly what I was looking for, Eric. So if you were a little nervous about that and you're sitting back there and going, I didn't know how they figured that out. The key to this, and the reason we have this mnemonic, is to pick through this English language and to pick through each statement. So the key word on that was of. Of. That key word of said, oh, this is an equality. This is an equality. I want to hit the calorie number right on. Of 2,000 calories. I'm targeting that number. So the calorie figure is an equality. What about the salt? Which direction is the salt going? Less than or equal to. How did you know that? But from reading the statement, what if you didn't know what if this was like some nuclear power equation? You had no idea whether this was good stuff or bad stuff. How would you know? What was that? Not exceed. So another key word, right? So we're reading English through here. And so not exceeding means less than. So we're going to do less than or equal to on this one. Very good. And then the vitamin D? Greater. Is it a bad thing? Is vitamin D a bad thing?
No.
But what if you didn't know that? Right? Let's just assume you didn't know that. You were ignorant. You had just been eating candy bars all your life and you had no idea what nutrition was. They give you another sticker. All right. Satisfying. Key word in the statement, satisfying. Hit the limit or above. You are satisfied. You get a full tummy, you're satisfied, but I'll take another one. You're satisfied, but you can go higher. So greater than or equal to.
You're
The other way, if we go more than 100%, it's going to be not good for your health, I would say.
I know, well, that's debatable, right?
Yeah, because you can't get too much vitamin C, or it's
You
like
can.
yeah, you can, but it's not good for your health.
It's kind of like a rule. If it's satisfying, it's always like
What do you mean by that?
greater or equal.
Right. So could you drink enough orange juice in a day to hit a vitamin C limit that would be hazardous to your health?
6 liters.
6 liters. You would spend all day in the bathroom, right?
Nice.
So,
Then you need to take more time.
yeah, so I mean, you're right. I mean, there is such a thing. I mean, if you were taking vitamin C pills, it is actually technically possible for you to have a toxic level of vitamin C. But obviously, that's kind of, we're way out here in this kind of, way extreme, kind of not real world thing. And clearly, if you were really worried about that, then maybe we'd add another constraint. Maybe we'd add another constraint that would say, oh, and by the way, vitamin C must be less than or equal to 500%. Just kind of picking a number out of the sky there, just making it up. If you really thought that was a potential risk. And you might also, honestly, in the real world, this is where your intelligence comes in, right? In the real world, you have this beautiful linear program. It churns and burns and generates a solution. And God help you if you just take that and hand it to the boss and don't even look at it. Right? I mean, you want to look at the solution you just generated and check it for reality. Check it to make sure that the numbers kind of are in the right sense, and maybe that solution comes back with, oh, and you're going to have 1,000% vitamin C, and you go, whoa, wait a minute, we don't want to do that. That's bad. We don't want to do that. And honestly, reality checking the linear program is what I owe my publication career to. Because my primary contribution to the literature, which we're going to talk about today in today's class, my primary contribution to literature came from my starting to do a timetabling problem, taking the solution and wanting to make sure it was really correct, And, oops, what did I do? I drew my own string line by hand from the solution of my linear program, just like you were learning last week. I drew my own string line by hand on a pad of paper while I was sitting there watching the TV, and I'm doing a little sketch, and I'm all fine. I'm like, oh, this is good, and then suddenly, this is not good. Because the string line I drew was infeasible. The string line I drew showed the trains crashing into each other. And I was like, what's wrong here? And at first I thought, oh, I've got a computer programming error. I made a mistake in my computer program. No, I hadn't. My computer program was actually correct. It was actually completely correct. And in fact, what I discovered is that fundamental assumptions about timetabling formulation were incorrect in the literature. And so one of my contributions to literature is showing that, unfortunately, some people's prior published models are defective and are not suitable for scheduling trains in a real-world dispatch environment. So anyway, we'll get back to that later. So, so we got our directions here, we got our stuff here, ready to go. We're going to write this. This part of the board from here over is in the correct kind of technical way to present a linear program. So everything from here over is nice and clean and real-world presentation. So the next thing you want to do to write on your piece of paper, or when you're typing this up in a manuscript or something, you want to write below this, you want to write down two little letters, ST, S period, T period. Stands for subject to. Subject to. It's just a little flag. It's just like, hey, here comes the constraints, guys. Look, here's the constraints. So we can do these in the same order that we did here. We do the calorie line first. So for each constraint, you need to have a function that calculates the value of the thing that you're limiting. And then on the right-hand side of that, you will then put the value that you need it to stick to, the value that you're holding it limited to. So we need a function right here that tells us the quantity of calories we are going to get with the decision that we make. What is that formula going to look like?
70x1 plus 110
So that is the value of the calories we would get based on the decisions that we make. That is the value of the calories generated from our decision. So this is a constraint line. This is a constraint function. And then it is going to be equal to this right-hand side. Right-hand side, it is going to be equal to 2,000. And then we go down the line, we do salt. We do salt next. So salt, what's the equation for salt?
X3 and 9x4.
Excellent. Now, another rookie mistake. You guys seem pretty sharp. You guys are pretty fast on the receiving pitch here. But a rookie mistake that young folks make doing this kind of thing, and I see it a lot back in the States, is doing this and being really nervous about this empty space right here. I see a lot of folks are like, ooh, I don't like that. There should be something there. I got to put something there. And I see it on exams. When I'm giving an exam, and the exam question, it says formulate this problem and write the formulation down here. And then I see all these tortuous attempts to make a number fit in that space. It's like, oh, there's got to be a number there. I've got to figure out what the number should be. All right. It is not going to be the case that every spot on the constraint matrix has something in it. It is not true. Some of these could be blank. Now, if it makes you nervous, if you're not really a math whiz and this makes you nervous, you are perfectly fair to put a 0 in. If that just keeps your head straight and keeps you from making a mistake and, just makes you more comfortable, put zeros in the places where there's not supposed to be a number, so they just keep the whole thing organized. But it can be blank or 0, it doesn't matter. And when you come to doing the computer program, the computer doesn't care either. So you can put a 0 in the computer program and it will still take it just fine. It'll just ignore it. It'll just wipe it right through. So here's our salt number here, and we said the salt had to be less than or equal to, and it's 100%. And then, of course, you guys are picking this up really fast, so we can whip right through here and do the, I'll just do the next ones because they're really easy. So we have now our vitamin D, nothing, nothing, and 10, and 10. And then down here, and this board's a little shorter than I'm used.
100%, so what? No?
Sorry? Well, these are, I didn't put these in as decimals.
Then you.
So these are whole numbers. So if I put them in as decimals, then it'd be 1, right? So it's just about, so if I put this in as 0.13 and 0.09, then this would be 1. But since I went with the whole numbers, we're going to go with the whole numbers. It, obviously doesn't matter to the, it's the same thing, just divide by 100 to the whole line. Good, but good. I'm glad you asked. Good. And then the last line here, nothing, and then 160, and then a nothing, and then 10. Now we're almost done. We're almost done, and this actually has all the information on it that you normally need to put into a computer program. We're almost done here. But there's one more thing on here that is technically required to make this real, and that if you don't do this on a written description or a page or a manuscript or something like that, you're going to get your hand slapped because you're not doing it right. The one thing that's missing on this is the non-negativity constraint, because this whole system works with an assumption that all of these variables are positive. They're all non-negative decisions. So we have this assumption down here way at the bottom. I'm kind of running out of space, but it looks like this. These are all non-negative. Or sometimes people will just write X non-negative. And some of you might be thinking, oh, but I can think of all kinds of real-world problems where the numbers are negative. But it doesn't matter because it's a piece of cake to just pick up your scale and shift it over and drop it down again and recalibrate everything so the numbers are suddenly positive. And then once you've got the solution, take the answer and pick up the scale and move it back over again and drop it back down and recalibrate everything back so that you get the negative number out you were looking for. So it doesn't change the method of the application. There are ways to manipulate this to deal with, I don't know, trying to think of a real world situation with negative. I guess deficits are negative. Refunds, I guess you return something, you get a refund, that's a negative. Kind of business situation where there'd be a negative number involved. Anyway, but now we're done. This is the whole written formulation for this linear program. This is the whole written formulation here. And questions? How is it going with the download? Is it downloading, or are you just sitting there staring at a spinning screen?
I'm waiting for your flash drive.
Okay, so it ain't gonna work. All right, okay. So let me put this on the flash drive, and we'll take a coffee break and let people pass this around, and you can eat it that way. That's how much content it really has. It's just a really white, totally unhealthy, fluffy bread.
Okay.
All right, so my hope is that I'm ready to go. I'm ready to go when you can get this screen up on your computer. When you have this screen up on your computer, now you don't have all those things on the left. Those are project files. But when you have your screen up on the computer and you have something that says IBM iLog Cplex and a menu bar and some structure of windows, they may not be the same as mine because this is my working copy of IBM iLog, and so I've moved my windows around. But when you've all got this up, we're ready to go. Does everybody have this up? Is anybody, I'm still waiting to do an installation?
Yeah.
Maybe one, maybe two. A little bit slow back there. And then, so I'm going to go ahead and at least get us to the point where we've got the model file in here, and you can watch, while you're watching your progress bar go across the screen, you can still watch what I'm doing. So I mentioned to you this diet file, so grab this in the data folder of CampusNet, USA Diet. This is the model file for this problem in IBM iLog Cplex, already done. So download that. You don't need to open the archive. Just get the archive file down onto your computer. Once you've got that on your computer, we can load that into the iLog Studio. And let me show you how that works. It's really simple. So you go File menu, Import, Existing. And I'll wait till you've caught up with me. File menu, Import, Existing, then get the dialogue that comes from that, and then I'll go to the next step as soon as I feel like people are caught up with me. All right, so Import Existing, and you get a dialogue that looks like this. You're going to say Browse, and actually let's go with Select Archive. Select Archive File, Browse, and my copy is Desktop, Lecture, and Diet. So you open that archive. So it should see the project, the Diet project. And then you say Finish, and it's going to add it to the palette on the left. It's going to add it on the left to your list of functioning projects. And there we go. And so it's added to the palette of functioning projects on this thing right here. And actually, if you want to make space on your computer screen, you can probably safely close any window that you don't see displayed up here right now. So if you're trying to make room and you got too many things open, anything you don't see up here, go ahead and close it. So you pretty much just need the projects window, a little window here that displays the contents of the files when you have them open, and then this window here which displays the progress of the solution when it's running the solution. Those are really the really critical things. Everything else is kind of a luxury, kind of extra. You can just close it, and you can get it back later if you really want it, but I doubt you'll need it for anything that we're doing. So USA Diet. Yes?
It is a model file that we open.
This is as far as I've gotten. And actually, I'll close those other two windows because they might be confusing you. Let me close these. Let me just close these. These might be confusing. So this is as far as I am right now. So there's the project installed. Have you got that, Christina? Have you got the model? You got that? Okay, great. All right. So that there is the model file in iLog Cplex for this diet problem on the board right here. And it's a really simple model, but this was an introduction to kind of get you, if you have no previous experience with this software, here's a nice basic kind of introduction to how to structure this. So in IBM iLog, there are a lot of different ways to do this, and you'll quickly learn that there's a lot of complexity that you can dig yourself into. But at the most basic level, you have a model file and a data file. And it's your model file and you have a data file. So here we have a model file and a data file. So the top is the model file, and we'll just kind of open that. Double click on it, it pops into the window on the right. And I'll kind of move this around to give us a little bit more of a view here. Kind of scoot this down, come on. There we go, whoop, nope, and right there. Kind of scoot that down. So there is our model. This is the model in what is called the OPL language. And just to give you a short history on Cplex, so Cplex is the gold standard when it comes to linear programming. This is a high-end commercial product. Any decent literature paper, any decent research paper, anything that ever claims they're making some improvement in linear programming, it's got to have a table that says, here's what our thing did, and here's what IBM Cplex did. That's like the gold standard. You're always comparing yourself against Cplex. It's been around a long time. It used to be a private company. Then IBM bought it like 6 years ago. And so it used to just be Cplex, and now it's IBM Cplex, but it used to just be Cplex. And iLog was the company that originally programmed Cplex. And then Studio, and then the OPL language, which is the kind of the syntax of this stuff here. So it's pretty straightforward. The model file has this top half where you're simply defining the names of the stuff you're going to work with. And then this ... business means get it from the data file. It basically means ... get it in the data file, look there for it. And then we come down here, we define the decision variable. This is a keyword, means float, means define a decision variable as a real valued number. And a float is a number in your computer that is How many bits? 24 bits? I guess it depends. How many bits is a float typically? Actually, it's not fixed, is it? It depends on the software you're using, doesn't it? Or is
No, it is fixed.
it is fixed.
Yeah.
It's like a 16-bit. Anyway, I think it's like a float is a number with a top value of like 15 million and something.
19.
It's got some number of digits. And then a double float is twice as many, et cetera, et cetera. And then this says float plus, which means it's non-negative. So here's our non-negativity already defined for us here. So the decision variable is a non-negative float. The decision variable is item, and the index is the 1, 2, 3, 4, the different food items in the index. And then here's our objective function right here. Minimize sum of these things, summation function of the items right there, cost times the item. And then down here, subject to, and then we have a listing, and I'll scroll down. And then here are our constraints right here. Sum, linear function, equal, sum, linear function, less than or equal to, sum, linear function, greater than or equal to, sum, linear function, greater than, just exactly like on the screen here. So there's the mathematical presentation. Here's IBM iLog's presentation. And this business where I named the constraints is optional. That makes the constraint name show up in a debugging report if you want to see it, but that naming of the constraints is not required. You could strip that out and this program would still run. So that is the most basic kind of example of a linear program in Cplex, in IBM iLog Cplex. Let's take a look at the data file. There's our data file, very straightforward. My biggest complaint about IBM iLog Cplex is the data structure is really a pain in the butt. It is not, it is, you know, the thing you got to do to make the data portable are so cantankerous. And I've tried it all. I've tried ODBC to a database. I've tried spreadsheets. I've tried all these things, and I finally have, in my most recent research, I have just bit the bullet. And I have written my own routines that punch the data out to a text file that looks like this. And then I have IBM iLog read my text file. It's just so annoying. It's annoying that they don't have a data structure that is just a simple kind of like comma separated values or something. They don't do that. It's very, very annoying. So it means a lot of careful typing and a lot of fooling around depending on what your method is. So here's our data file, and you recognize most of these numbers should match the numbers over here. And let's run this. Let's run this thing.
There's a mistake.
That's right, and we're going to see the mistake. Yeah, let's see that mistake pop up so you see what happens when you need to debug your model. Let's do that. So I'm going to scoot. This is the model view down here. And now, the way this works is you then define something called a run configuration. And the idea behind this is that you could have a project with a bunch of different models, and you could like create different go buttons to start different models and kind of mix and match what's going on. But in this case, we've only got one model and one data file, so there's only going to be one configuration. So let's do this. So here's our configuration. There's our default configuration. And you say right-click, and you say run this. And it runs it.
Can you press this green button? in the
You
top?
can, but then you have to like stop and say, wait a minute, is that the configuration it's going to run? Because in my models, I've got all these configurations, and I forget. It's like seems like it's helpful, but it's not really helpful. It's not really helpful because the last thing you want to do is hit go and discover it's running the wrong model. Thank you very much. That was not very helpful. So it's just so much safer to just go over here and right-click and say run this because I know for sure I'm running the right model. You know, especially if it's a model that's going to like run for half an hour and it's going to like write all these files to your disk. You don't want to hit the wrong one and come back later and discover it scrambled all your data and you don't know what it
have
did.
this function that break.
But I would have to know it was the wrong one. What if I hit go and I went and got a coffee and I came back? And I'm like, where's the answer? It's not safe. I don't, it's not really that helpful to me. I might use it if I were running the same model over and over again, then it makes sense maybe, because if I were just churning the same model, go, 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 then okay, maybe that makes sense. But I don't do it that way. I typically, I run it once and then it runs for like 6 hours. And so I need to know it's right. I need to know it's right. So run this. And actually okay, so it has an error. So this first tab is the debugging window, right? Now I know there's an error because I put an error in this purposely to show you that there's an error. So if you click on the error, it'll say, hey, there's an error. And you click on it, it says, hey, this is because I'm not connected to the network, I bet. Let's see if I'm still connected to the network. Am I connected? I am connected. Why didn't it want to run? Let's try it again. Is anyone else getting the same error?
I've got 2 errors.
Yeah, you should have at least one error, but this isn't the error I was looking for. This error is saying that my license is no good.
Are you connected?
Press on the Chrome window on the browser. It's yellow or something like that.
I mean, my internet browser says I have a connection. And you guys, you're running the model and you're not getting this error.
No.
So why am I getting this error?
No, sir.
Well, let me see. Let me show you what the error is. And I've also found, this is also very annoying, I've also found sometimes that iLog will give me the wrong error message. I've been using this product for 8-9 years. And it's so annoying that it has this weird memory dump thing where it'll give you an error message that's not related to what the error is. And you discover that it's like a memory overflow over here from some other function in your model, and it causes the error message to appear over here. So let me fix the error and see if this solves the, or actually I could just run a different model. I guess I could, so for example, if I run this one, no, it still doesn't like the, I bet I have to close and reopen.
Yeah.
Hope I don't have to restart. That would be a pain in the butt. Hmm.